Chemistry Department of IIT Indore. So today we are pleased to have Professor Sundargopal Ghosh from IIT Madras to deliver a talk on the structural paradigms in metalloboron chemistry. So before the start of the talk, I would like to briefly introduce Professor Ghosh to all the students of IIT Indore. We know him for a very long time, but for the students actually, this introduction, a very short introduction. He graduated from the Science College, Calcutta in 1993. And then he obtained his PhD from IIT Bombay in 1998, where he worked on the Fischer carbene complexes of group 6 transition metals and chalcogen stabilized diiodine clusters. Then he went to University of Notre Dame for postdoctoral studies, where he developed new synthetic routes to hypoelectronic metalloboron clusters. And after completion of his postdoctoral tenure for 5 years, he took up the position in the Department of Chemistry at IIT Madras, where he is a full professor at present. So his work mainly deals with the transition metal boron compounds. That includes the supra-icosahedral clusters to electron-precise transition metal boron compounds, which have been successfully employed in small molecule activation. And he has published more than 200 research articles in highly respected journals like JACS, Angiochemistry, Chemical Science, Chemcom, Inorganic Chemica, Organometallics, and many more. And he has been, he is the associate editor of the Inorganica Chemica Acta. He is the member of the editorial advisory board of Organometallics since 2018. And he has also earned many accolades, like he was awarded with the Professor Priyadaranjan Roy Memorial Award in 2018, and with the bronze medal of the Chemical Research Society of India 2012. And he is a fellow of Indian Academy of Sciences, Bangalore, and also fellow of National Academy of Sciences, Allahabad, in 2017. So I would request Professor Ghosh to deliver the talk, and we are really eager to hear your presentation. Yeah.
Okay, thank you very much, Dr. Sharma, for very nice introduction. And very good evening, and welcome to this special lecture series on Acharya Prafulla Chandra Roy. And before I begin, I would like to also thank this Department of Chemistry, IIT Indore, for asking me to deliver a talk on this special lecture series on Acharya Prafulla Chandra Roy. Well, I mean, this is very special because, this Indian Chemical Society came a long way, and this is one of the very oldest societies in this country. And I am also very actively involved with this society, and this is really very nice of all these initiatives that has been taken. And last 10 years, this society is doing extremely well, thanks to some of the very active members, in particular Chittoda and our president, Professor Vaidi Yadav, and many others who made this society into what it is today now. Okay, so let me share the screen now. Is this okay?
Yes, yes.
Okay. So my topic today that I'm going to talk is structural paradigms in metallo-boron chemistry. Today I have decided to talk on this particular topic because of some of the very latest development that we have recently from our laboratory. That you will see it when I talk about these molecules in a little bit time. However, for the benefit of the students, I would like to just spend a few minutes about the milestones of the boron chemistry. Many of you, you all read in the textbook about a hydroboration reaction, Boranes, all those Mingo's, Witt's rule. But there are many other molecules that many of you might not have read because they are not been listed in the textbook yet. So there are many more applications of this, these molecules having boron. This is used in hydrogen storage material, in cancer therapy. There are many drugs also have boron there. Boron nitride, carbide are very useful material. And then you know that the daily uses of this, the glass that contains almost 10% of the B2O3. And also this carborane, there are a lot of polymers with this molecule. On the left-hand side, you see this is a superacid made from the carborane. So a lot more applications with this boron compound. You know, this is one of the very important molecules of boron, that is a borophene. You know, the Nobel Prize on the carbon, that was a graphene. So graphene and borophene is not too much of difference. Only difference between these two is that it has a hexagonal hole in the middle. And because of that, borophene is extremely interesting material, is much better than the graphene. The only problem with this material is that someone needs to make it in quantities so that you can use this material for different applications. So unfortunately, this is still at the matrix isolation stage. So maybe in future, if this material can be made in quantities, and this could be a game changer. Then this is a MgB2. You know, this was known for a long time, but no one has studied this material about this property as exciting superconductor. So there are many more of this boron compound. So we have been working on all these, the metal borides, clusters, with an objective of to have them in a different applications. And as you could see here in these slides, the recognition in boron chemistry, there are many. It started from A.C. Brown, where you know that the discovery of the hydroboration reaction, and then the Lipscomb for the boron bonding, and there are many more. Hoffman for the isolable analogy, that very well connected with this boranes. And my favorites are this, which is listed in the red, that is that Waits-Mingo's rule. Then you have your Lipscomb and the Hoffman isolable analogy, and of course that Mingo's fusion and James MNO. So these are the different the things that in the milestone I consider that helped me to give a shape of this boron chemistry for the last 24 years. Okay, so and more you know about these different of their contributions, you will typically, you know, like get into this field and you'll see the contribution of them into this boron chemistry, particularly in cluster chemistry. Okay, so as I said, that my topic today I'm going to talk is the metalloborans. For the benefit of the students, I would like to just take few minutes. What is metalloboran? Organometallic, you all know, when metal carbon direct bond, we call organometallic. Then you have a boron carbon, it's a carborans, and compounds having metal and boron direct bond, we call it a metalloboran. So I'm going to focus today my talk on this inorganometallic, in which you have metal boron and other main group metal bondings. Now, very important thing about this uh, this element boron is a very typical, like if you look into the periodic table, this is exceptionally different from any other elements known in the periodic table. And boron being next to carbon in the periodic table, carbon actually does not have too much of like structural varieties that it offers. However, boron being an electron deficient molecule in terms of it does not follow any of the electron counting rule, particularly like carbon, it follows the octet rule, boron doesn't. And because of that, boron can offer a varieties of bonding that carbon cannot. As you see here, in this you have a different kind of bonding, starting from your sigma borane, sigma borate, augustic complexes, bis sigma borate, many more. And utilizing this property of the boron that participate in the 3-center or 4-center 2-electron bonds, we have made a tremendous number of these molecules that shows a very, very interesting structures and geometry. I'm going to talk some of them today in this lecture. This is some of the molecule here I have listed that very nicely the boron compound mimics the classic organometallic species. The first one, as you see here, is a B2H6 that very nicely mimic your C2H4. This is the ethylene. Then you have your B3, then you have your B4, then you have a B5, then you have a B8. So all these molecules see the same number of electrons as that of the carbon counterpart. And you can consider this as a direct mimic of these organometallic species. So this, the pentaboron, as you see here in the ferrocene, it was made by Russell Grimes in 1977. So this reminds me of the story of this pentaboron 9, which was one of the very exciting molecule of boron series. And the US Air Force wanted to make this molecule for this United States and Russia having this Cold War in 50s and 60s. They wanted to make this as a rocket fuel because it has almost 3 times more energy compared to the other hydrocarbons. So what they did, the US Air Force research base in California made a huge amount of pentaboron. And what happened, somehow this program, this rocket fuel program got failed, and they had to destroy all the pentaborans they had stored here at the Edwards Air Force Base in California. As you see here on the bottom, these are the pentaboran tanks that typically, although it looks a little smaller, almost at 500 pounds of liquid. And so they made more than 5,000 of this kind of tanks. So they had no other choice, but these are highly explosive compounds, so they had to destroy it. So before they could destroy, they're looking for a potential lab where they can gift this pentaboron so that they can do some research. I remember that in the 90s when I was in the US, and I knew many of Tom Fellner, who was directly into this program, and I believe they got a lot of this pentaboron tank with this liquid as a gift. I believe the condition they had from this US airports that you cannot give you 1 or 2 liter of it. You have to take the entire tank to do your research. So I think there are a lot of stories I heard. I'm not going in details about it. Let's get into this. Another mimic, that is your single boron, in which you have a borylene, the very important one. I'm going to spend some time today to talk about a borylene, how this molecule got stabilized in the coordination sphere of 3 metal. Okay, so this is all about like the history, this and that. But when it comes to the synthesis of these compounds, typically the starting material we have been using it, that is cyclopentadiene metal chloride or metal carbonyl or some of the metal chloride precursors. And you treat them with a lithium borohydride at very low temperature, and depending upon the transition metal, the reaction might lead to two direction, releasing boron or hydrogen. Now the precursor for this metal of boron, starting from early transition metal all the way up to the late, they are very difficult to synthesize, and also they're highly air and moisture sensitive. And this could be one of the reasons why this chemistry, like is confined to only few groups in the around the globe. Okay, so nonetheless, we have been working for more than 16 years in this field, and having all these difficulties of handling these compounds, somehow we managed to get a very interesting molecule. So the main reason I wanted to show you that there are two types of chemistry it undergoes. One is the left-hand side, the late transition metal, where the metal has fill of electrons with a d orbital, where in the early transition metal, in which you do not have enough electrons, so they have no other choice but to take the hydrogens from the lithium borohydride and give a very different kind of molecule. And the late transition metal, they typically lead to the formation of case molecule, what you call so far is a closo or the nido kind of geometries. Okay, so isolobal analogy, this is one of the very important discovery. And using this isolobal idea that permits metals to be substituted for the BH, utilizing this, we had utilized this molecule. This is ruthenium 2b2, is a butterfly. We wanted to see if one of the BH vertices can be replaced by this isolobal FeCO3 fragment. Indeed, it works. And as you see here down, we have made a series of molecules utilizing this concept, and in which this BH is stabilized by these different metal carbonyl or cyclopentadienyl metal fragments. And this is also a true mimic of this organometallic species of the cobalt-3 carbonyl. We made a review of, we made so many molecules. So a few of my students made a review during this pandemic, and that appeared in this year, middle of this year. Okay, now we move to another very important molecule, that is a diborane. You know that diborane, banana-shaped molecules, you all read it in the textbook. So we wanted to see whether this diborane molecule can be stabilized again at the coordination sphere of a transition metal. So the left-hand side, what you see, this is the molecule made by Sheldon showed a long time back, 1989. In which one of the hydrogens is replaced by FeCO2 fragment. We also made a similar kind of molecule, not exactly the same, in which again it's a diborane 6, where the hydrogen is replaced by the Cp ruthenium fragment. And formally it's bonded to B2H5 system through a single 3-center boron ruthenium boron bond. Okay, so once we had this, we wanted to see whether we can do something with group 6 metal. We started with one of the molecules made by Simon Aldrich long time back. And we treated with the carbon monoxide with this molecule. And what happens, as you see here in this formula, it's a B2H4. The proton as well as the boron NMR at room temperature, as you see, it's a completely flat. If you keep lowering the temperature and you go to -80, you see the metal HB as well as the 11B chemical shift. So this molecule is highly fluxional, and we are fortunate to have a crystal structure for this molecule in which the BB bond distance typically a single bond 1.698, where you have a B2H4 and one of the hydrogen is bridged between these two boron atoms. Now this is again a classic a mimic of a acetylene molecule made by F.A. Cotton in 1978. And this molecule, again, it was made by CpMoCO2 dimer. And when it was treated with acetylene, it leads to formation of this acetylene. And this is again exactly same as that of the B2H4 molecule. Now this B2H4 you can consider to be isolable with your acetylene. And we believe that this gives 4 electrons to this the metal fragments, and indeed it does. I'm not going in details. James did a lot of calculation for this molecule. And now interesting thing about this diboron 4 is that, so there are 4 different types of diboron 4 molecules are known in the this was proposed by James sometime back in a Dalton Trans paper, in which he had shown there are B2H4 where you have a D2H, you have a CS, you have a D2D, and you have a C2V symmetry. And what happens, all these 4 molecules except the CS symmetry was not known structurally. So this now fits very well, which has a 4.0 kcal per mole in terms of that energy is consumed. So once we had this B2H4 as a tungsten CO4 is a 2 electron fragment donor to the cluster bonding framework, we wanted to see whether this could take the 2 hydrogens from the B2H4. We treated this with tungsten CO5THF and other metal carbonyl fragment. Indeed, when it reacts with this, it takes 2 hydrogen and with the replacement of tungsten CO4 fragment. This you see the tungsten CO4 fragment. Now the interesting thing about these 2 molecules, so the left hand side with the tungsten, the BB bond distance is 1.71. And in this you have 1.59. So this is a single bond and this is a double bond. So you can consider this molecule as a diborane. That is, diborane molecule is extremely unstable unless you stabilize it at the coordination sphere of the metal. So this was a very nice a demonstration how you can make a diborane to diborane using a metal carbonyl fragment. So we had also utilized these things. I will show you in a bit. Now, this is another very good example of a classic diborane 6 molecule. You know, there are 2 types of molecules, as one is the classical, another is the non-classical. Classical structure typically are very, very rare. Non-classical one, particularly when it comes to the diborane 5, there are many molecules been synthesized by many group, starting with Sheldon Shore. We also contributed, Holger Braunschweig, Malcolm Green. So in which you see that in the non-classical mode, you have a BHB. So, so these kind of molecule, there are many more known. We made one molecule that I have shown some time back that was a B2H6, where one of the hydrogens of the B2H is replaced by the CP star ruthenium fragment. So we wanted to see whether any of this classical B2H4 minus fragment can be stabilized. So again, while working on a tantalum system, we have isolated one compound that NMR shows at 2, one at 34, another one is at -11. And we were anticipating that could be a Diborane 6 molecule. However, based on the NMR, it was very unlikely. If you look into the different B2H6 molecules that James came up with, and the B2H6, that's not the lowest energy molecule. The lowest energy molecule is the one at -15.4, which is the most stable one. And if you look at it, the X-ray structure, it shows exactly the same, in which you do not have a B2H6, but you have a B2H5. Another hydrogen, it is not connected with the boron fragment, but with the metal. Now, the reason we have been struggling almost a year to figure it out what is going on, we have never anticipated that tantalum H tantalum can be the positive 9.26. Most of the metal H metal that comes at a negative region, and we had no idea that this is, we always ignore this peak as impurities. So anyway, so that was a very fantastic retro kind of calculation that James did, and that made the entire thing in a very crystal clear. The structure, everything matched very well. So once we had this B2H5, so this is the first B2H5 minus molecule, classical one, the stabilizer, the coordination pair of two tantalum fragments. So this I have shown you. Now, in the same year, Douglas Stephen also had synthesized a Diborane 5 cation. This is the structure, B2 2-diborane. They made it from this Diborane 4, but treated with a tetraethyl silane toluene cation, and that gives your Diborane 5 cation, which is very stabilized. And this is the first structurally characterized B2H5 plus. So we have the same year, you have a diborane anion, and in the same year you have a diborane cation. All right, so as I said that once we had this, the excess hydrogen, we wanted to see whether the two of the hydrogens, the way we made a diborane 4 to diborane, we wanted to treat them again with a molybdenum CO5 fragment and to see whether this can take two hydrogens. Unfortunately, what it does, it coordinates simply with one of the boron atoms, and you see that you get a simple adduct. And this is the X-ray structure in which you have the molybdenum coordinated with the this tantalum. And once it coordinates with one of the boron, and the boron chemical shift goes further downfield, that satisfy why this diborane 5, it was coming at a very that low field boron NMR. So now if you look at the molecule of this molybdenum CO3 connected to the boron, there was a possibility of fluxionality, and based on the calculation, and it shows that this might shuttle between these two tantalum. And indeed, when you lower the temperature, you could see very well that this molecule is actually fluxional. As you see here in the metal HB, it splits into 3 different peaks, and here also CP star split into 2 different tantalum. Okay, so this is the one I wanted to spend some time today. Like a diborane 6 planar molecule since after the discovery of the benzene. Most of the people who have been working in the boron chemistry, as I mentioned there earlier, it was a dream to make a flat B6 ring. A lot of calculation, I had listed some of them here. James Lai Seng Wang, Alex. There are many more theoreticians. They wanted to make a flat B6. Some of the examples I had listed here, one of them, there are matrix isolation, and some of them they had proposed theoretically. So what was a recent study, not recent, it's a very old study rather, it was 1988. James proposed that a possibility we have investigated is to create an inverse sandwich structure in which B6H6 can be stabilized with a CP vanadium or CP titanium fragment. And the result is a triple decker sandwich. This is not my statement, by the way. C5, H5 vanadium tantalum B6H is this. We have worked on it, and here in the picture is crystal clear. You can see this now. We have been working on this field for a long time to have this titanium B6. Now this is a dream come true. When you treat this titanium Cl3 Cp star, you get a B6. This is a single boron peak. This is the metal HB. We have done all the possible spectroscopic data. We have recorded the low temperature. We have done a different experiment to see if any kind of fluctuality is involved. This molecule is extremely stable. There is no fluctuality whatsoever. What you see here in this geometry is that, so alternate boron atom, we have a titanium HB very nicely, and it's very stable. It does not move at all. So it is exactly not planar. It's almost planar. So this is a very recent result that we got, I think, probably a couple of weeks back. However, in the same time, as you see that the Cameron Jones in 2018, he made aluminium 6H6 molecule. And that molecule is not a planar. This is a typical octahedral molecule. However, this is the first time he has isolated a aluminium 6H6 molecule. And another student of mine, Anagha, she was working on vanadium chemistry, where she had isolated the same molecule again with a CP star vanadium fragment in which you have a B6. So this is not a crystal clear to us yet about the hydrogen and the other connectivities because there's some disorder involved. We had sent this molecule to Ellison Edward at a nephron diffraction unit in Sydney. The data has been collected. Hopefully, in future, we'll be end up getting the neutron diffraction data for the same molecule, and we'll be able to share this. So these are the very two exciting results of this vanadium B6, which was proposed long back by many theoreticians. And now it looks like we are going to towards that. Okay, another few molecules that I would like to spend. One is the B7H7. If you look into the textbook, you see this B7H7, or you can call it hepta borate, is missing, mainly because these other the borate anion like B6 to B8, B9, 10, 11, 12, they have been known for a long time. It started with, you see this 1959 by Frederick Hawthorne, followed by many of the pioneers of the boron chemists, including Lipscomb. But the B7, the problem was the moment it was formed, it immediately goes to the B8. And it was very difficult to make this molecule to isolate and structurally characterize. However, in 2011, Barnard made this molecule with a counter ion as a tetrabutyl ammonium. And we have been working on this molecule. This is the first time we have isolated a B3H8 stabilized at the coordination of two zirconium CP2 fragments. The moment we had that, we wanted to see whether the other higher borate anion can be stabilized. This is the one we could see that the boron NMR is a bit complicated. So once we had the mass spectrum followed by X-ray structure, as you see here, this is a very clear heptaboron, a bicapped pentagonal pyramid. This is stable, neutral molecule, and the stability for this molecule comes from the presence of these two zirconium Cp2 or the hafnium Cp2 fragment. We have done calculation in collaboration with Lai Seng Wang at Brown University. I am not going in details, just to convince you that these two fragments gives enormous support to stabilize this B7, and that's the reason we could isolate this. Another molecule recently we made, again, as I said, that our objective was to isolate the higher borate anion to this coordination. So we made B3, we need B7. Now we also have isolated a B8. The beauty of this B8 study is that this molecule is a decaboron, and this decaboron molecule, if you look at the different geometries of this has three different molecules. One is a bicapped trigonal prism, you have a square antiprism, and you have a dodecahedral. And in all these exist in the solution as well as in the solid state. However, there was no clear information about this NMR, both in the solid state as well as in the solution state. In solution state, the existence of dodecahedron structure is still a mystery. However, once we have the structure of this compound, it's very clear from the NMR that this dodecahedron also exists in the solution. We have done calculation in collaboration with GEMES, in which it shows a good percentage of the electronic contribution to this octaboron from the metal Cp star fragment. Okay, so to summarize this particular chemistry is that now we have isolated some of the borate anions. Now our objective is to see whether a supra-icosahedral B13 or B14 can be stabilized utilizing the same strategy that we have achieved with the B7 or B8 isolation. So hoping that in future probably we'll get some success, if not the supra-icosahedral. All right, so my last part of my talk, I'm going to talk about a cluster in which not many of the textbook has listed. That is a geometry beyond icosahedron. Okay, so this is a very well-known geometry. All of you know that icosahedral geometry, the maximum number of vertices that the boron B12 known. So there are a series of studies by Lipscomb, Shaler, GEMES that shows the possibilities of a higher borons beyond icosahedron geometry. However, as you see here, the icosahedron geometry is the most stable one. Nonetheless, the other geometries with the B13, B15 or B16 is also possible. And there are the two different types of calculation done by Lipscomb, the Shaler, and they have listed it here. So this table clearly shows that utilizing some kind of synthetic skill, you may come up with this barrier of this icosahedral, the supra-icosahedral. So we have been in this race for a long time. The main problem with the metalloboron chemistry is that whenever you get a higher vertex metalloboron, so there is always a tendency to have a cross-cluster metal-metal bond. And because of the presence of this cross-cluster metal-metal bond, this becomes highly electron deficient. It doesn't follow any electron counting rule. And that also does not give a regular shape in terms of the geometry is concerned. Okay, there was a lot of theoretical studies by again, Shaler, James, and Lipscomb. As this studies was made by James, what he proposed that as boron cannot offer a more diffuse orbital to be placed in the axial position where you need a higher connectivity vertices. So he proposed that if you can have a metal fragment which could be isolable to BH, there is a possibility you may get a higher vertices geometries beyond icosahedron. This was also proposed by Frederick Hawthorne, and it's a very typical a cluster build-up reaction starting from a carborane, and this is just I copied from a Greenwood textbook. It shows a sequential cluster build-up. You just treat with the sodium THF, and then in naphthalene followed by cobalt Cl2 sodium Cp, and you end up getting a higher vertices geometries. So we used it. However, in our case, we could not do anything. But when we try to pyrolyze this Cp star metal chloride with the lithium borohydride and boron, as you see here, this compound, this is actually, I'll come back in a little bit. I'll show you how this the geometry can be described. So we have got that geometry, and that is nothing but a truncated tetrahedron in which 4 of the hexagonal faces are capped by a 4 metal fragment. So if you take typically a tetrahedron, if you chop all the 4 vertices, you generate a truncated tetrahedron that will have a 4 hexagonal faces. Now the one we got in this is a 4 rhodium atom that cap all the 4 hexagonal faces. So this is a tetracap truncated tetrahedron. First time we have isolated this as a single case higher vertices geometries. We extended this one because this was a proposal made by Lipscomb long back, that if you can also do this chemistry with a cobalt Cp, and the proposal was that it was a Cp Fe, Cp cobalt 4 times with a B12. So we did that. We don't get it, but it ended up getting a different fuse geometry. So these are the 3 molecules later on. I think this year, I'll just show in a bit. This year, a good friend of mine in Hong Kong, Zoe Z, he made this molecule, which is also a 16 vertex carborane, and which has a different geometry than ours. Okay, and he also succeeded another 16 vertex metallocarborane, which has also a different geometry. So you have 3 different geometries of a 16 vertex, or this is called square crown square. This is a truncated tetrahedron, and I don't remember how we call this 16 vertex geometries. Okay, so this is the one I was talking about. In the cobalt case, you get a fused geometry that can be described as a fusion of a icosahedral, a bicap square antiprism, and a tetrahedron. And this follows very beautifully both Mingo's fusion formalism as well as James MNO. I'm not going in details. Whenever we get a cluster, this is our some kind of like exercise, and I also sometimes give this to that MSc elective course to count the electron of this very complicated system. And I remember some of the students also made this both Mingo's as well as MNO calculations. So this is a very good, like a textbook example. Of course, it's a elective. You cannot do this in the textbook normally. But it very nicely gives a challenge to, first of all, you have to describe this geometry, followed by the counting the electrons using this different formalism. All right, so this is the one I was talking about, made by Zoe C with a different strategy from a carborane. And again, the same strategy, it has been applied. You treat this with the sodium THF, you generate, open it up to NIDO, and you close it with another B boron vertices. And again, you do the same strategy using this. So this, this looks very simple. I remember that 2012, I visited Hong Kong, his laboratory, and he got this molecule last year. And that time he was telling me, oh yeah, we've been working on this molecule to make a 16 vertex. So now you know the challenge for almost more than 10 years to get this molecule into the reality. Okay, so with this, I think I would like to summarize my talk. I hope that I tried what different structural paradigms of the metalloborane species, and that classically mimics many of the organometallic compounds known in the literature long back. Some of the molecules I have shown here, this is a very classical mimical of the ethylene, and then you have a B6 molecule which is almost a planar. Then you have your borylene, then you have your pentaborane, so on and so forth. And this is a very latest example. Recently, we have isolated. We are going towards the next step, that is a 17 vertex molecule, single case cluster. As you see here, this is a 16 vertex. You can call it as a NIDO or a fuse. We need to look into this, whether there is a bond exists between these two boron. Now, whether we can apply a DSD, diamond square diamond rearrangement, to remove that bond and get into a single case or not. That's, we are working on it, and we'll see if one of the vertices can close this to get a 17 vertex. So with this, I would like to thank all the people. Without their contribution, the work that I presented today was just not impossible. The Diborane chemistry I presented today, it was made by Bijan Mandal, who is now a Humboldt, with Manfred in Regensburg, Ranjit, who just finished PhD, Kaushik, who's another Humboldt with Holger Braunschweig. Saurav and Anagha made the B6 molecules, and also Saurav made the, and Shubhas Boiragi, who also made the, who is in this picture. Shubhas Boiragi here is sitting, who converted from MSc to PhD. Gitarani Shubhankar's contribution to the tantalum chemistry, particularly with the BH borylene work. Yuvraj, who made also in the same field. Deepak actually made the discovery of the first 16 vertex clusters on the rhodium. And my collaborators, without their help, the work I presented was just not possible, particularly with the GEMIS. And and LS Wang for the heptaborane work, and the crystallographer Babu Varghese and Sudha Devi for their enormous amount of help, particularly with Babu Varghese. Most of the molecules that we synthesize have always a disorder, and to clean this molecule to have a very clean structure, it's just not possible without his help. And finally, the funding from DST, ACRB, CPIPRA, CSR, BRNS, and IIT Madras for continuously supporting to do this fundamental chemistry that we have been working here for more than 16 years. And thank you very much. And I will be very more than happy to take up questions if you have any. Thank you.
Thank you for your excellent talk. I hope you won't mind to take few questions.
Sure, sure.
Yeah. So, students, any questions? Else? Maybe I'll ask a couple of questions. Yeah, I can relate with my PhD more.
Yeah, I remember.
Yeah. So this diamond DSD, diamond square diamond mechanism, which somehow means was difficult for me to accept actually this mechanism. I always felt this is a very complicated mechanism during at least my PhD. So did anybody calculate a barrier for such DSD mechanism? I mean, I'm just curious how much the barrier. I mean, I always felt that this is a really difficult one.
Well, I mean, see, I mean, you are asking a very wrong person, Vishwajit. You know my theoretical knowledge. But nonetheless, what I know, not many molecules have been tried to justify. One of the molecules that they had tried is that, like a carborane, ortho, meta, and the para. That was a typically DSD rearrangement they had to come up with. And also some molecules, like I remember that when I made the first time rhenium B10, that does not follow any geometry. So they and Tom had to apply 3 DSD to come up from your typical icosahedron. So this is just to like play around with the geometry. I don't think that people are very serious about these energies of the different DSD isomers that they could come up with. And I like probably I won't be able to comment much further on this DSD rearrangement. But only thing, like you have a geometry, you apply a couple of DSD or single DSD and see that your geometry is getting there. So then you're happy, but theoretically, that energy difference and all those things, I don't know. I won't be able to comment much on that.
Okay, my second question is this iso-level analogy one. So you have a lot of metal-based complexes, right? So can you find that all the cases this iso-level analogy follow what BH? I mean, mainly you replacing BH with a metal or metal ligand-based group, right?
Mm-hmm.
So is it applicable for all the cases iso-level analogy?
See, our approach is, like whenever you cannot apply, like all those big molecule and you isolable, you cannot have this fragment in hand. Okay, so they need to be generated, like in the reaction mixture, either thermolytic condition or photolytic condition. So now if you have a bigger clusters and then treat them with cobalt fragment like CO2, CO5, it gives 4 electrons, 4 electrons, 4 or 5. And then you have a CP cobalt or FeCO3, ruthenium CO3. So these fragment needs to be generated in the reaction mixture itself. If you start with something with a very smaller cluster, you may consider that possibility to replace by this isolable fragment, and it goes. We have been practicing this, having a simple, say, like octahedral or a butterfly geometries or a tetrahedral. We treat them with a typical metal fragment, anticipating that BH or the CH or some fragment could be replaced by this, and it follows. It very nicely follows, replacing this BH with a isolable metal fragment. That comes sometimes with hydrogen also.
Yeah, so my maybe similar question, maybe in the same line, like how many of your like synthesized metal boron complexes you have used isolable analogy and synthesized?
Typically, I mean, many are there, but once we have the molecule, have the excess structure, then you claim it, or we made it. But like although we had an approach, but like it's much easier later on to claim that okay, that was objective and we got it. But yes, on the background, this was always in our mind that this might form. I would not claim that we purposely did this and got that. But yes, it was in our mind that this might work out as a replacement of a particular fragment with isolable. There are many, but mostly, as I said, no, that's small molecules. With a bigger cluster, it's very difficult. Like if you have a decaboron, many of the decaborans like B10H14 or their analogs, it very nicely follows. You can simply cap them with isolable BH fragment. Very nicely it follows. And recently, like we have been working on the decaboron system, and I have been asking students, you just use this fragment, there is a possibility it might cap as a 6 connected vertices and you can get a closure structure. And indeed it works.
Yeah, I think I'm done. Anyone else?
I have one question. So, what about the stability of these higher order clusters? And that means C16 or C14, B14 or B16, whatever.
See that higher vertices clusters and particularly with a late transition metal, they are fairly stable. You can actually do column chromatography using silica gel, or if you are rich, you can do a TLC with aluminum foil. But like as we work with the rhodium chemistry, these are the starting material. We start with 50 milligram, so we cannot do a normal column. So we do a thin layer chromatography using aluminum foil. So they are fairly stable. Their closure structure. The moment you have more hydrogens, then it's difficult to pass through them in the silica gel. It die there.
Any other questions?
Yeah, I have one. Like your tantalum case, where you have wanted to replace your hydrogen with tungsten, if I remember correctly.
That's a molybdenum, right?
Yeah, molybdenum. And have you ever tried to replace that hydrogen with base and add up the gold PPH3 fragment so that it's in 1 electron fragment and you end up succeeding there?
Well, Deepak, we are not that much of interest just to make a gold adduct. I think typically it is possible. Hopefully, we have not tried that. It should be doable, but I don't know. I mean, what we do with it.
As you were testing that hydrogen can be replaced and you make a beat.
Yeah,
Yeah.
I believe it is possible. Maybe it's a good suggestion. I can ask. The yield is of this molecule is not mass, so that could be a challenge. But yes, that's a good suggestion. But but at the end of it, but it just to get adapt, just to foolproof your, like approach or strategy if it works or not.
Another one like your that like a NMR temperature one, variable temperature NMR, where you showed there is no change in the variable temperature NMR when you lower the temperature.
You're talking about this?
Yeah. So have you ever checked to go up in the temperature, like higher temperature, whether this?
No, this is one thing we need to see. I told you, this is just last week or last week result.
Okay.
And getting NMR slot, it's also these days difficult because a lot of group, only one machine. Still hitting, we need to do it. Yeah, we need to do that. We have planned.
Okay, yeah, that's all from my side. Yeah. Thank you, sir.
Any other questions? Okay, if there are no questions, let me thank Professor Ghosh for his excellent talk on borons, fellow borons. That I thank you again.
Thank you for asking me to be part of this very special lecture series. I know this is very special. This Acharya Prafulla Chandra, I have been associated with it as the guest editor in the special issue. And it's really thankful to the people who are now making this Journal of Indian Chemical Society to coming in a big way. I think they are on track. Very happy that this initiative, they made it. Very nice. Thank you so much for asking me again.
Thank you then. Okay.
Thank you so much.
Okay, bye.